All right. Okay, perfect. Thanks a lot. Really appreciate it. If the recording, if there are some issues with it, I'll definitely reach out. So hello guys. Welcome to the first literature week of our new monthly development cycle. And for this monthly development cycle, we'll be looking at the papers. This paper, Implementation Matters in DeepRL, a case study on PPO and TRPO. So the paper is currently being accepted in the um, ICLR, International Conference of Learning Representation. I think by the time we were originally looking at it, it was under blind reviews, but I think now the authors are actually shown right now. Yeah, so it's those people, and apparently most of them are from MIT. And the core idea of this paper is that it says the PPO's code level optimizations, which is algorithm augmentations found only in implementations or described as auxiliary details to the core algorithm, have a major impact on the agent behavior. So the authors further conclude that they are truly responsible for the trust region enforcement, which is this core idea of both PPO and TRPO algorithms. And before we jump into the paper, there's something that I would encourage all of you to check it out, especially if you're interested in joining the implementation weeks. So it's a guy was implementing PPO, and I was looking at his repository, and it seems he actually implemented a lot of the tricks that are mentioned in the paper. Of course, in the paper itself, they also published their code, I believe. It's here. But I think their code is a bit harder to understand. I may be wrong. I haven't exactly looked into it yet. But just some resources that to keep in mind. So let's get into the papers. So mainly, the papers list out about 9 different code level optimizations that they really think could potentially help the PPO, and they suggest it was not the PPO's clipped objective that's really improving the agent's performance. So the first technique is called value function clipping. So initially, how you train the value function is you use the value function of the current minus the value of the target. The target values, I believe, is the discounted returns minus the values. But I'm pretty sure. But either way, when they do the value function clipping, they actually clip it uh, to avoid the losses being too large or something. So that's the first technique that they use. And the second technique is called reward scaling. Um, Right. So they actually have a rolling discounted sum of rewards, and they normalize the rewards by using the standard deviation of the rolling discounted rewards. I think they do the same thing with the observation as well. And the third one is orthogonal initialization and layer scaling. So from the code perspective, I'm pretty sure it's this. It's this part. Where you initialize the norm, the weights of the layers differently. I think the default initializer is Xavier, but they suggest using the orthogonal initialization is also one of the technique that the PPO implementation uses. And they also have this, the fourth technique is the atom rate annealing. So what that is that the initial atom learning rate is probably 0.0007, and then as time goes on, it becomes 0.00001 or something, so that they hope that the optimizers will be more robust as the game goes on. So that's the fourth technique. And the fifth technique is to clip the rewards within some sort of preset range. That's kind of an interesting one in my perspective because different environments really have different definition of rewards, and this just seems kind of arbitrary, especially 5 or 10. It would make more sense if they um, oh, actually, yeah, okay. So they must have done the reward clipping first and then do the reward scaling. I have to look into the details of their code to determine which one it is, but that's one of the technique listed. And the sixth technique is the observation normalization. Like what is being said here, in a similar manner to the rewards, the raw states are basically normalized to by using by using a standard deviation of a rolling statistics of all of the states. And analogously, they also have this observation clipping. And lastly, they also, sorry, the eighth one is that they use hyperbolic 10 activations, which if you look at the code here, when they do the forward, they most use the torch 10 H, which is the activation function apparently that is selected in the PPO implementation by OpenAI. And lastly, they have this gradient, global gradient clipping. I don't know whether they have it in this paper, but in ClingRL, in the common code base, it's very easy to do the global gradient clipping. It's basically here, the neural network package utils clip gradient norms, so that the norm of the gradients don't exceed certain amounts. And I think this is very common in the OpenAI code base as well. I see it everywhere for each algorithms. So those are the ninth technique that the authors mentioned that are present in the OpenAI's PPO implementation, but not really mentioned that much in the PPO's original paper. And they found that these some of these techniques they prove empirically that, well, they did some experiments and showed that some of these techniques are more responsible for the agent's performance improvement than the clipped objective of the PPO algorithms. So then they did some experiments. So those are some of the techniques. So for example, initialization, that's the orthogonal, and the on the y-axis is the rewards that is being received in I think this is Hopper environment. I could be wrong, but it's one of the gym environments, continuous action space. And as you can see, usually when you try out those techniques, the agent will perform better. So for example, when you normalize the rewards, the and compare it to not normalizing the rewards, the agent receive less. The agent that doesn't do the normalization of the rewards, they perform worse than the agent that normalizes the rewards. And the similar things that happens with a majority of those techniques as well. The only thing that doesn't really make much of a difference, it seems, is the initialization and the value clipping. I think. Right. Mm-hmm. Mm-hmm. Right. But eventually it gets better, right? Right, right, right. So I think if you can't see that, that means the agent never receive any rewards higher than 600, let's say. Right. So in that case, the annealing actually really helps a lot. Yeah, actually, it turns out that annealing and normalizing rewards turns out to be some of the most powerful techniques, right? Because you see a lot of red in them, and with the initialization, it's more hit or miss. Like it doesn't really help with the bottom environments, but it helps a lot with the first environment. Yeah. Well, you also have to realize that they're running this ablation study that has so many factors, and you usually also want to try to run algorithms on those experiments using different seeds. So it's a combinatorial explosion. Once you start to play with more parameters, the number of experiments you have to do just kind of increases so much so quickly. So they decided to do further experiments, and they want to see if the clipped objective actually helped the PPO to learn. So they propose a couple methods. So they have the PPO, which is a regular PPO algorithm that use the PPO clipping objective and also use the all of the optimizations that are mentioned above. And they also have PPOM, which doesn't really use the code level optimizations and only use the clipping. And they have the PPO with no clipping and optimizations. But yeah, just read it. Hopefully this makes sense to you. And in my opinion, they actually have I guess, the new algorithms in some sort of way, which is the TRPO plus, where they added the PPO optimizations. And here are some performances. So let's take a look at the y-axis. So the first one is the mean reward, and it turns out the best performing one is PPO, just a regular one with the optimizations, and the PPOM, which is, remember, it's the one without the code level optimizations. It just performs the same as the regular TRPL. In other words, without the code level optimizations, the PPO and TRPO's performances are fairly similar. So probably not a lot of improvement by just the clipped objective. And here, the y-axis is the maximum of the probability distribution in the next time step over the probability distribution of the last time step. I think this is a measurement of the how different are the probabilities from each other, and the PPO with the code level optimizations is performing best because I think this is the trust region bounding that they were talking about. Because with the code level optimizations, the policy doesn't move that much. I actually don't quite understand why they have a K out here and a max pi theta over pi 0, because KL is also a measurement of the differences between different probability distributions. But in this case, it's the same, that without the code level optimizations, the KL divergence just kind of diverges. And while the PPL with the code level optimization still stay within the trust region boundary. And the quoting from the paper, it says it turns out the code level optimization alone enforces a trust region without clipping the objective function or explicitly bounding the distance between successive policies. So that's a very interesting conclusion. And then they did further experiments. They want to know, is a clipped objective the root of PPL success? And the answer is no, because when you see the PPL without clipping, both in rewards and as well as KL divergence, when you don't have clipping, it's just not really performing as well as PPL with optimizations. And lastly, they did a little experiments with TRPL plus, in which they added the code level optimizations, and they found the TRPL plus to be very comparable with the PPO with the code level optimizations. So in a couple of environments, TRPO is only performing worse in the humanoid task, but they also don't have a lot of tasks. This is just 4. So this is basically a quick rundown of the paper. Anyone have any questions, things you would like to discuss? What do you get? Yeah, go ahead. Hmm. Right. One thing that's here's the thing. Apparently, because this is the open review, they apparently are constantly modifying the final camera version, I guess. And at some point, when I was looking at this, they only have four of these remaining, and then they just say the rest of the techniques is discussed in the appendix. But I think in their latest version, they found that was an error, and they just added the techniques that they neglected back into this section. Uh, but yeah, yeah, yeah. Potentially, yeah. In the newer version, this should be fixed. And but overall, I think they only experimented with a couple of these techniques because they claim that experimenting doing this ablation study with all of the um, techniques will be very computationally expensive, and they don't have the resources to do that. Yeah, which is kind of a shame. It would definitely be more interesting to see how the agent performs with more ablation studies. Like, for example, I don't. So for the observation normalization, I think that's probably going to be very important as well, but that's not mentioned in the paper. And also, there's something that is not consistent with the paper. Like, notice here, it says valid clipping, and here is just valid clip, but just some minor details. But yeah, so this is the bulk of the paper. I think it's definitely very interesting. When dealing personally, when I was dealing with a continuous action space, um, it's always very difficult to debug. And when I look at PPO's implementations or a lot of other people's implementations, they always do things differently, and they have various code level optimizations or tricks. So for example, with the A2C. So this is the A2C continuous script. With A2C, one thing that I found eventually made it work was to make the. So does anyone know how does A2C generate continuous values for the action space? Okay, yeah, not a problem. I can give a quick rundown. I definitely want you guys to be uh, keep you guys informed with those things. But essentially, with the continuous action space, let's say you have three values that you need to generate for a car. Uh, the um, the angle that you're turning and the acceleration. Um, let's just use those two values as an example. The way A2C generates those two values is that they create essentially four numerical values. The first two are the means, and the second two are the standard deviations. So they use the means and the standard deviations to create two random variables, and they sample the acceleration from the first random variable and sample the angle from the other random variable. And because those are random variables and they're probability distributions, you can calculate things like the entropy and the log probability, which is sort of the whole theory behind how to optimize over actor critic algorithms or policy gradient. So that's how they optimize it. It sounds very simple, but when you actually do it, it turns out you have to make the logarithm, the standard deviation independent from the states. So that's a very interesting thing that I definitely was not aware of. And when I don't do that trick and just run the algorithm, it just doesn't really work. When you see the performance, it's just a straight line. The agent doesn't really learn anything. So yeah, with continuous action space, I feel it's more difficult and more difficult to experiment, more difficult to debug, more tricks in general. That's probably one of the reason why in the PBO's paper or in this paper they mentioned there are so many techniques with PPO, especially dealing with continuous action space. Yeah, yeah, of course, go. Mm-hmm. No, actually, no. So soft actor critic is the algorithm that we just implement for the last development cycle. And actually, this topic is briefly mentioned in the spinning up page as well. Let's take a look. So here, if you look at here, the policy, yeah, so first of all, they use 10, and the way they calculate the loss probability is also a little bit different. But also here, the way standard deviations are parameterized. In VPG, TRPO, PPO, we represent the log standard deviation. Yeah, that's another thing. So you don't just output the standard deviation, you output the logarithm of standard deviation, and then you use the exponent on it to get the actual standard deviation. Like if you're just starting out with this topic, it's like why do you do that? But there hasn't been exactly a very clear answers to that. At least personally, I haven't found like a very plausible explanation, but it just seems to be the things that works. But anyway, so we represent the log STD devs with state independent parameter vectors. In SAC, we represent the log STD. I don't know what this devs is. Uh, Probably just, oh, standard deviations, right, right. I was talking about developments. Yeah, log standard deviations as outputs from the neural networks. So they, in the SAC, they also do it differently. And they very nicely ask you, can you think of why? Or better yet, running experiments. Mm-hmm. Mm-hmm. Right. So for that, first of all, that definitely sounds very plausible, but that would also be the case with the A2C continuous as well, because so first of all, you can always optimize it. Like if you make the standard deviation independent of the states, the you essentially have the standard deviation as the neural network parameters themselves, so you can always optimize over them. Yeah, but this is just seems to be one of the mysteries, and I actually look it up this topic in their repo, see if anyone posted an issue about this, but no one has apparently. But yeah, this is definitely something we can look into in the following weeks to see if there's a better answer to justify. Okay. Mm-hmm. So for your first question, about the normalization, um, uh, I wouldn't know what would be like a best value for it. Like if you think about the way they normalize the observation, it's a rolling normalization. So like whenever it receives an observation, it'll append it to a list, and then as time goes on, when you receive a new observation, you just say observation. Yeah, how do you normalize things? Observation minus the mean over standard deviation of the observation list, or something like that. Is that right? Um, yeah, I guess there isn't a concept of a best value for normalization. And, yeah, yeah, go ahead. Yeah, go ahead. Hmm. Yes, yes, of course. Um, so there's definitely maybe more techniques. You can make the means and standard deviations of the observation list, the rolling observation list, to be, I guess, less abrupt. Um, yeah, I don't know how that's gonna affect the agent performances, but definitely could be something that um, we could research into, right? Mm-hmm. Mm-hmm. Oh, really? I see, I see. Uh-huh. Mm-hmm. Right, right. Yeah, defining rewards is definitely a very tricky issue. Like the RL problem in some way almost becomes a reward engineering practice. Um, yeah, for sure. Um, but yeah, so feel free to jump in and comment and ask questions at any time. But I think so uh, for the next step, if people are interested, we should definitely start taking a look at the code and try to implement some of this. And for those of you who haven't participated in the monthly development cycle, especially the implementation weeks, what we would recommend is to take a look at some of the files in the folder. Um, and then when you try to implement the ideas in the papers, try to keep a lot of the common structures. Like, for example, you put the common arguments here and algorithm specific arguments here. and you try to keep the seeding as well, so that if you're running into some issues, and when we try to exchange files, we could have really good reproducibility. Um, and also just a gaming loop in general. Try to keep a lot of the things so that when we compare notes to each other, it will be easy to do that. Okay. Yeah, yeah. Please, yeah, please go ahead. Uh-huh. Yeah. So currently, when we run more experiments, it would look something like this, where um, we use the XVFB run dash A because we want to actually record the videos of agent performances. I don't know if everyone has seen this, but right now we're doing a more complete benchmark with all of the agents' performances. Is this something that you had in mind, or like a very specific, a different kind of configuration file? Okay. Right. Right, right. So the my issues with the configs files in general is that um, when using a lot of the config files, first of all, they kind of introduce a different an a, it introduced new complexity to the code. Like if you just want to try something out very simply, you have to write a file and pass that file and parse through it. But more importantly, what I usually found is the configuration files. They usually are not general enough, and it also hides a lot of important details from you. Like for example, the I guess maybe that's not an issue with the config files, but when I was trying something out like the rllib, and they have a configuration file, and that's just yeah, it's like this. It's vastly complicated and doesn't show you any code. You sort of have no idea what's going on except to read the comments, and it's very hard to do any sort of customizations with them. Like if you want to mess with the agent's behavior. Yeah, that's sort of the reason I'm not a big fan of it. Um, yeah, but if mhm, mhm. Right, right. Yeah, that's definitely helpful as well. And in the common code base that we have now, it's been sort of built into this help function. So if I do, oh, actually, since I'm only sharing one screen, actually, yeah, I could be able to do that. Yeah, yeah, exactly. It's just as simple as that. And my thing is freezing up. Yeah, this is my computer at work. It's pretty bad. Yeah, so if I do dash dash help. Yeah, it's just a standard Python argument thingy. Oh, yeah, it just shows everything as well. And then it's also the fact that you know the configurations are matched with each individual files directly. So yeah, with the configuration files, it's also sometimes the case you have configurations that applies to other algorithms that does not necessarily apply to your current algorithm. Um, but yeah, if you like it, feel free to build something up and see if you can make it as simple as possible to use, and let me know, and we can definitely discuss different possibilities. Mm-hmm. Right, right. Mm-hmm. Right, right. Mm-hmm. Right. Yeah, so I would say unless there's a real good use case for using a configuration file, let's maybe just stick with what we have now. Um, yeah, yeah, not a problem. Thanks for bringing that up. Yeah, the other thing, I don't know if all of you guys have seen this, but where Rosalind and I have been doing benchmarks in the uh, in sort of a okay in sort of a more interactive manner. So now you have this, which I'll post it here in the chat real quick in the Google Hangout here. Wrong thing. Yeah, but feel free to check it out. So that's a benchmark of all of the current algorithms that we have. But also, this is a new thing that we added. We use the gem monitor API to record the agent's behavior at each time step. And then you can click on here, for example, to see what the agent is doing at step one. And as you can see, the card pull is just really shitty. It falls almost immediately. But if we go to the train steps, it balances a lot better. And that's also the case with a variety of different games. With the mountain card, we can see which algorithm that actually solves it. So for example, in this case, the DQN performs the best, and the other ones are just stuck in a little valley here without never able to get out. Um, and with so I think this is the current one that Rosalind is working on, the PPO continuous V. Uh, may, may, and it's performing really well. Maybe maybe he can share with us some of the things that he did with this file. Why is it performing so much better than the other files, right? I mean, if you have like short comments on, not explaining the whole algorithm, but is there like a particular part you did that makes it work so much better? Okay. Okay. Yeah, it definitely seems the case. And the other thing that, would be really helpful, if you guys want to look into it, is assuming I can drag this thing. Okay, I give up. So if you open it, and you can actually go to the files here, and then just download the file that is responsible, right? So that's also a way that I try to make reproducibility as easy as possible. No, 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 it's fine. Whatever works. But eventually, when we integrate things, it's better if we have the similar, if we have similar style, and if there are reasons to adapt different styles, we can definitely talk about it. Like I have been thinking about adopting. I'll talk about that later. After, but yeah, just checking out this repository. Let me know if it blows up your computer because so many videos are being loaded. Um, I actually, yeah, the one that I really like is the lunar lander. When you see the agent's performance of the different steps, like initially, it always crashes. Yeah, but eventually, surprisingly, almost all of our experiments algorithms converges, and SAC is performing the algorithm that we implemented seems to the one that's performing the best. We also have a domain that's also kind of interesting. It's the taxi v3. I don't know if anyone has worked on it, but DQN seems to be one of the only algorithm that's able to solve it. The other ones are stuck into this local minimum where, yeah, they just couldn't get out of it. Taxi v3. I encourage you to try it out. And if you're really stuck with the problem, ask me about it. I actually know there's a way to train A2C to um, make it learn such that it goes from here to here almost immediately, but that's not a general technique. So yeah, but yeah, if you want to talk about it, let me know. I don't want to give you the answer right away, but you know, you should try it out and we can have a fun discussion about it. Spinning up. Yeah, one thing that I've been thinking, but I haven't got the time to do so, is to do this. So like a style change, which may be for the better or for the worse. Actually, I think it's going to be for the better, of course. But so if you look at this, the stepping style, like how you run the whole thing, uh, I was really impressed with the SAC's cleanness. So what they do is they say for T in total number of steps, and then just run it. And then if it's done or if it exceeds the maximum length, then you do something. So that's a lot cleaner. But they interestingly they also don't have a unification of style. Like for example, here this is more similar to our style. It's for each epochs and for the maximum numbers of time steps in each epochs do things. I think this way is cleaner. I don't know. What do you guys think? Which way do you think cleaner? The SAC style or the PPO style? Uh-huh. It's off policy. Mm-hmm. It, but it wouldn't make a difference, I think. Yeah, PPO is online, but that shouldn't be a problem. So what you would do is, um, right. So for if it's online, if you look at the SAC style, what you would do is at the end of this episode, if it's done, then you do the updating, right? Yeah. So it would still be online. It just so if you look at our current implementation, it has certain things that I actually, it's pretty clean too, but like it, like it, yeah, you have the if dones and stuff. So essentially, yeah, so essentially the what? Hmm. Okay, I see. But yeah, I was just gonna mention if we're using the new style, the SAC style, essentially this part of the code will go into here, and that's it. Yeah, yeah, exactly. That's basically the only things that's going to be need change. I think it looks cleaner, but I mean the current. Yeah, go ahead. Sorry. Yeah, so that's another technique, right? Are you talking about the what's it called? Yes, yes, right. You append it to the end of the returns, right? Yeah, that's a technique that I've seen. Yeah, so we can definitely experiment with it to see if the so we can create different files like PPO, Bootstrap, and see if that see if that improves the agent's performance. The reason why I didn't include it was because a long time ago I was actually experimenting with that with the A2C, and what I found is that the bootstrapping doesn't seem to be helping at all. So, like if I run the same experiments, what I found is that the actions that are being executed is almost identical. So like literally the same. So that's why I was thinking maybe the bootstrapping is not it's not improving nor deteriorating the agent's performance. It just doesn't have any impact. But maybe I would be wrong in different environments. So, yeah, yeah, that sounds great. Feel free to do so. And, we can study different things and see how if they help the agents or not. Um, but yeah, this is what we have right now. Hmm. Hmm. I think you meant like code level optimizations rather than the objective clipping. Yes, yes, I think that's the main idea of the paper is that the code level optimizations actually them right, it's this sentence, right? It turns out that the code level optimizations alone by itself enforces a trust region without clipping the objective function. These eight techniques together. Yes, I think so. Or or yeah, yeah. Hmm. I think it's mainly these four techniques: the valid clipping, normalization rewards, annealing, initialization. And actually, this guy, uh, let me see if I can find it. Um, sorry, what was that? Mm-hmm. Mm-hmm. Yeah, I think that would be definitely interesting, and we have the resources to do that. Just keep in mind that the more things you want to compare, the number of experiments you want to do will probably blows up exponentially. eventually, yeah, eventually you might have to decide which are the techniques that you're really interested in on. Let me also bring up something. I don't know what I'm just gonna put it here. Right. So I'm from China, and this guy is a very famous researcher in the field, and so this is something that I find a lot of inspirations from. He actually did a ablation study as well. So this is the result, and what he found is that the no advantage norm, which is, I guess, the reward normalization, turns out to be the factor that's impacting the average rewards a lot. And something else that really is really important is state normalization, right? Yeah. So yeah. Yeah. So I think this is Mujurko, right? Yeah, it's half cheese topper. Yeah, it's Mujurko. And if you look at it, the state normalization is one of the techniques that this paper is not addressing, which I find it to be a shame. But but it's like this is a blog post and this is an actual paper, but they're talking about the same thing, and it's very inspiration to me that even smaller things that seems it's just a blog post could be written into a paper and could be very constructive as well. It's all about yeah, it's all about the deepness of your research and whether it solves a particular problem or explains a certain situation. Okay. Um, Anyone have any last minute questions or comments? Yeah, go ahead. The what? Hmm. For the PPO continuous? Right. Okay. What about it? Okay. Total loss equal to policy loss times the I think that's a I don't know, but I think that's a very common practice, right? So do I do the same here? Let me see. Yeah, more or less. So I have to confess something. At the time, I was so frustrated with the PPO in the continuous case. I actually just kind of copy a lot of code from this guy, and I was really interested in knowing what was exactly the components that made it work. The total loss. Oh, the value function coefficient. Hmm. Right. Mhm. So my comments on that is it wouldn't be much of a clipping. It would be more of a scaling because you're not cutting it off. You're scaling it down by using the coefficient, right? But so you see here, so this is the A2C, and they do exactly the same thing. So this part is sort of copied from the OpenAI implementation. So this is the A2C. I just kind of do this similar tradition with the PPO, but I'm almost positive that it's going to be the same thing. But we can take a look. And it's interesting they have two PPOs. Like, what does that even mean? Oh, I see, I see. Like the returns minus the value function is the regular advantage, right? Right, right, right. Yeah, so if you see in the code, they also do the same thing with the PPO. So that just seems to be a very common technique, which I don't know if that's going to be like if the yeah. Yeah, probably. Yeah, that that sounds good. Yeah, go ahead. Yeah, go ahead. I'll disable my screen right now. Go ahead. Okay. I can see your screen right now. It's fine. Uh-huh. Mm-hmm. Right, right. Mm-hmm. Mm-hmm. Right. Mm-hmm. No, 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 no. So go back to the last page. So so the advantage is just scalar values. So it shouldn't have any gradient. The gradient comes from the policy. So the pi theta a over s. So it comes from there. The gradient. Mm-hmm. The advantage. Go ahead. Uh-huh. Yes. Uh-huh. 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 Let me see. Let me see one more time. So the minimum. Could you go back? So it's the ratio times the advantage. Minimum of those two. I think about the minimum advantage. You're right, because the minimum advantage doesn't have any gradient, right? It's just the no. So can you open a PPO implementation of mine in the CleanRL code base and take a look at the clipping thing? Oh, by the way, for everyone else, if you feel the need to, if you need to go, please feel free to do so. The meeting is over. But Rosalind, feel free to stay and we can take a look at this. Yeah, just PPO continuous will be fine. So you have the ratio, which is that, and then you have the surrogate. So I think I'm pretty sure I do it differently, and yeah. So my two surrogates would have gradients into it because it has a ratio, right? Yeah. So that's yeah. So that's so your ratio still have the gradient. So actually, let me see. So the first part. Oh, sorry, yeah, it should it be like ratio times the advantage pH, and the second one should be ratio times the min advantage, right? Wait, let me make sure, let me make sure. So you're right, so that's not a problem, but I'm looking at this. Why is one, could you go back to the so on the left side of your screen, could you go to the ratio? Okay, let me take a look real quick. So, minimum advantage. So for the minimum advantage, it's only doing a clipping on the advantage, and that doesn't make a lot of sense. Because when you do the clipping, you are clipping on the ratio, not yeah, doing that on the you're not doing it on the right thing. The clipping is. But the ratio shouldn't even be there. The ratio should be in the minimum advantage variable, right? Because the one plus clip ratio times the advantage, the one plus clip ratio shouldn't be with the advantage. It should be with the ratio, and then after that's been completed, then you times the advantage, right? So essentially, you have right. So you have your ratio, and then essentially you have your clip ratio, and then it should be ratio times advantage pH, comma, clip ratio times minimum advantage, right? Yeah, I think we should also start a issue. Since you discover it, you should probably let them know. I think this is definitely a mistake. Okay, okay, feel free to do so. Okay. Thanks everyone for coming. Um, Appreciate it. And if you can, please join the implementation week. If you're into messing with the implementations, Rosalind and I are very invested into this. We'll be more than happy to take a look at your code. Um, yeah, for me, it would be really helpful if you try to keep a lot of the common structure. It'll help us to examine your code to figure out exactly which part are different. Um, but yeah, Oh, by the way, if you're doing the implementation, try to, since there are 9 techniques, right? So in the comments, try to say hashtag one dot value clipping. So you sort of annotate the techniques with the comments. Please do that. I think that'll help a lot, if that makes sense. But yeah, thanks for everyone for coming, and I hope you have a good weekend. And next Friday, we'll see you next Friday, 5 p.m. All right. All right. Thanks a lot, and see you. Yeah, you too. Thanks. Bye bye.